with glycolysis. And this chapter is on glycolysis and gluconeogenesis in particular. And once again, you are expected to know all of the steps. I don't require, I had to memorize like the proposed electron pushing and all that kind of stuff. But you need to be able to recognize that if I put in the reactants and the products, for example, you'd be able to know the enzyme name. If I put the enzyme name and either the reactants or the products, you can work backwards. So you're going to be given the structure of something. You don't have to memorize the structure per se, other than you've already memorized glycerol. From that, you can figure out some of these just because you should know glycerol. All right, so let's see. Okay, don't show me that one again. Nope. There we go. All right, so in general, I want you to know overall what's going to happen in glycolysis. So what converts to what? There are 3 possible fates for pyruvate. You're going to know all 3 of these possible fates. And I don't know any other way other than just to memorize the 10 steps of glycolysis. Once again, once you learn the logic behind it, it starts to make sense. Perhaps it just starts to make sense after looking at it for 20 years. But I did put the links up here for various animations. Some of them are slow, very simplified. Some of them will give you the enzyme names, just clicking. I don't know that this will let me do these. We will find out, see if it will let me. That is not it. No, still not it. So on your own, since it's not letting me go ahead and do the clicking, but on your own you can look at the various animations as it goes through. The overall scene for the glycolytic pathway is there are 10 steps. However, what happens is halfway through it becomes bifurcated because you have to double everything. Because what happens is, how many carbons does glucose have? 6. It has 6 carbons. How many carbons does a pyruvate have? 3. And so that's why you end up with 2 pyruvates. So whenever it breaks from being a single molecule containing 6 carbons to 2 individual molecules containing 3, it's almost like a choose your own adventure, because you're going to find out that's when it bifurcates. You have to then remember that steps 6 through 10, you multiply everything by 2, because you're going to have 2 of each of the molecules going through. And that's why this is attempting to show the fact that we have, 1 glucose, but you end up with 2 pyruvate. Okay. And you're going to see some of these common intermediates. This is fructose 1,6-bisphosphate, but you're going to see some common intermediates between glycolysis and gluconeogenesis, but gluconeogenesis is just not a simple reversal of glycolysis. There are some extra steps. Then we have the 3 possible fates for pyruvate. Many times, the most common being the fact that you can go through anaerobic oxidation, which is the citric acid cycle, the oxphos electron transport chain, and ultimately fully oxidize it all the way down to carbon dioxide. So that way you get as much energy out of it as possible. However, there are 2 other possibilities, at least in some organisms. One for us is under anaerobic conditions, we go through anaerobic glycolysis, and it ultimately goes to lactate instead of carbon dioxide. So what conditions, don't just tell me anaerobic, but under what conditions or what cells would undergo anaerobic glycolysis? When are we not going to be getting enough oxygen in order for it to go through the citric acid cycle? It's the muscle. So if you're working out, feel the burn, you literally are feeling the burn because lactate is really lactic acid. It's just a carboxylate form of it. So that's good to replenish it for short periods of time, but you can only do it for so long before it becomes detrimental. And then certain organisms, usually not humans, you can undergo, whoops, hit the wrong one again. That's going to get really annoying. You can undergo, or not you, but yeast, for example, can undergo anaerobic. Stop doing that. Anaerobic alcoholic fermentation, which is where they regenerate the NAD plus and they go to carbon dioxide and ethanol. I said not humans usually because there's this one medical study that I found in a journal which was awesome, where there was a guy who was going, and he was like a deacon in this church and everything, and he was hospitalized in the hospital for alcohol poisoning, and they couldn't figure out because he said, they could try and tell him and his wife that he's an alcoholic and it's because of all this alcohol he's consuming, and he's like, I don't drink. And his wife says he does not drink, and come to find out that he had an abnormal yeast population in his gut, and it was undergoing alcoholic fermentation and producing this alcohol. And so essentially he was getting drunk, but it wasn't from drinking alcohol, it was from having yeast infection. So, oh, it was in the blog. I don't remember, but I remember it was an awesome story.
Yeah, it was
So,
it's funny, he's like drunk in church. And
yes, he got drunk in church. It was more than the spirit that was moving that day. So, but a bum, Pentecostal humor. All right, so glycolysis is a series of 10 steps, 10 enzyme-catalyzed reactions, where you take the one glucose and you make 2 pyruvate. By the end of this, you are going to know what the structure of pyruvate is, just because there is an easy way for you to memorize it, because it actually, another way that you can get pyruvate is from an amino acid. I'll just tell you that. What amino acid will give you pyruvate, like directly, that you already know? Give you a hint. The R group is right there on the left-hand side of pyruvate. It's not aspartate. Aspartate has 4. It's not glutamate. Glutamate has 5 carbons. What amino acid goes directly to pyruvate? It only has 3 carbons in it total. Not glycine. Glycine has 2 carbons. Alanine. And so that's why if you draw your good friend alanine, so I'm going to try to do this on here. So alanine, C, CH3, where the amino group would be for alanine, you just turn that into a ketone or an aldehyde. I should say ketone. Because that's pyruvate. Okay, so that's why the aminotransferase that transfers the alanine, the amino group from alanine, will always make a pyruvate. It's one way that we can make pyruvate. So that's why I say that it's easy to know the structure for pyruvate. All right. There is also a net conversion of 2 ADP to 2 ATP. So what is the whole purpose of glycolysis? What is its purpose? Sounds like my phone. Consuelo may have an idea.
Producing 2 pyruvate.
Right. Like, what's the just overall purpose? If you were going to try to say this in simple words, what would it be?
Convert like the glucose to a smaller compound that's more reactive.
Nope, not quite.
Like the cyclic structure?
No, that happens really, really simple. I mean, early on, I should say.
Break down glucose into usable energy.
Okay, that's the Miss America kind of question, but we're getting close to it, because usually people say it's to make ATP. That's actually wrong. It's not very good at making ATP. It only makes 2. And so the important thing is it actually makes NADH. NADH is what goes on, skips ahead to the electron transport chain, and that's where you get your bang for your buck. And so we'll find out that for every NADH you typically get, for every mole of NADH, you typically get 2.5 moles of ATP. And so under most conditions. And so that's why you get a lot more from the NADH. And it does prepare the pyruvate. The pyruvate for faith integration is like Moses in the Holy Land. It cannot enter in to the citric acid cycle. And so something has to happen first. And then the citric acid cycle will produce even more, equivalents, these reducing equivalents, and then they all go to the electron transport chain ultimately. All right. So as I mentioned before, pyruvate is then metabolized into one of three ways. This is just a non-cartoony way of doing it, to where we have, okay, I'm getting a, not now, why in the middle of this would the stereo want to send me a little message? All right, so where pyruvate can go one of three ways, and under aerobic conditions, which is by far the important one, is it's going to ultimately go on to make carbon dioxide and water. Okay, and then under anaerobic conditions for muscle, we can go on to make lactate, and we're going to find out that's whenever you're working out to where it would be too long to replenish the oxygen. Okay, and we've got to keep the balance of NAD plus to NADH is of tantamount importance. Okay, because it's just not something that you can just eat more of. We actually have a very limited pool of NAD plus and NADH. So because of that, there are times that your muscles are working out and you can't be fully oxygenated. And so for brief periods of time, you can go under anaerobic conditions to get your NAD plus back, and then, lactate. And we'll talk about the Cori cycle later on. And then finally, yeast, in particular, can undergo anaerobic conditions using fermentation to ultimately make ethanol alcohol. So similar to like the brewer's yeast idea. So now we are ready, and this is the way that I like to do the metabolic pathways, where I hide something, these little ominous boxes, and you have to try to figure out using logic. And so obviously we start with glucose, which we're going to find out you don't always start in the beginning, because there are feeder pathways that can skip some steps. Salud. All right, so we have a glucose, which by the end you probably will even memorize or remember what glucose is. It utilizes an ATP, and we get two products, glucose 6-phosphate and ADP. And make sure that you remember how the numbering occurs with the glucose. And technically, this is going to be, you would talk about the alpha, beta, and all that kind of stuff, right? So this would be a beta glucose since it's on. I'm sorry, this is, let's see, if it's on the same side, it would be alpha. If it's on the opposite side, same side, and the tail is up, same as beta. The opposite would be alpha, so this would be alpha. All right. So we have glucose, we make glucose 6-phosphate at the ATP. Using the logic that we know thus far, what class of enzymes could this be? This is a kinase. So if you were going to name this, what would you think would be the logical name for this? Glucose 6-phosphate kinase could possibly be one name. What could be another name? That was if it's named after the product. What if it's not named after the product? Glucose kinase, which that's really, really, really close. And there is one isoform of this, which is called glucokinase. Just keep that in your head for much later on. But there are at least four isoforms I can think of. Sometimes they're just named after the broad class of compounds because they're more promiscuous. Like maybe it takes more than just glucose. So if we're just going to talk about what class of compounds glucose is, what's one way we can describe this? What class of compounds is glucose? Besides a sugar. Besides a monosaccharide. That is true. What else is it? What class of sugars is it? Hexose. This one is hexokinase. Okay, and we're going to see hexokinase a lot because the name alone should tell you that. And if you wrote hexokinase on the quiz, I'd give you most of all the points. Especially as we go along, then I would expect you to know more. You should have also ascertained why is the magnesium important, and anytime that for the cofactor here, how would we know that, it's going to require magnesium?
As you said, magnesium is almost in every single one.
Not in almost every single one, but it follows along when there's something in particular that's there. What does the magnesium do? Where would it be at? With the phosphates, especially with the ATP, GTP, stuff like that, you can almost always know that you're going to require magnesium. Okay. And many times, even if the magnesium is not listed on there, you can say it's going to require magnesium in vivo because we have plenty of it around. Okay. So we have glucose 6-phosphate. So now the little scorpion's tail has been phosphorylated. This is a very, very important reaction. This is one of the rate-limiting steps. There are 3 checkpoints in glycolysis of the 10 reactions. This is the first checkpoint. It is very much energetically favorable, considering the fact that it hydrolyzes ATP. And if you remember from last chapter, delta Gs are additive. And so it's not energetically favorable just to put an inorganic phosphate on glucose. Inorganic phosphate is perfectly happy by itself due to resonance. It's less happy actually attached to the glucose because it loses some resonance. And so the way that we get this to pay off overall is we couple that to the hydrolysis of ATP. Okay, so it's just like making an investment. With money, you have to make investments sometimes with energy to get energy out of it. It takes money to make money, so to speak. I don't expect you to memorize the actual number, like, under standard conditions it's negative 16.7. No, but I do want you to know that step 1 is a checkpoint, and it's hexokinase. All right. Now we're up to step 2. Which we take glucose 6-phosphate to fructose 6-phosphate. And this one actually has 2 acceptable names. And one of the ways, another thing that you will get used to seeing is the abbreviations that are used. So we started off with glucose. Technically, that was hexokinase. Now we're going to have fructose 6-phosphate. Sometimes they abbreviate stuff like that. Okay, so for the second step, what class or classes of enzymes can possibly describe this? An isomerase. Okay, and so if you were going to name this one, what would you name it? A pentoisomerase? Okay. What else could it be named?
Hexoisomerase.
There's a hexoisomerase. What if we want to be even more specific this time? Glucose 6-isomerase. Oh, you're getting really close now. You are very, very close. It's phosphohexosisomerase or phosphoglucose isomerase. Some books just call it specifically phosphoglucose. And so that's the reason why if you had said glucose 6-phosphate isomerase, people would actually know what you're talking about. It's like, okay, yeah, it's a phosphoglucose. But you don't want to forget the phosphate because it requires a phosphate. If you don't have the phosphate there, it doesn't work. So that's why this is technically, phosphoglucose isomerase. I've heard it called phosphoglucose isomerase, phosphohexose isomerase.
Doesn't matter.
No. For me, I would take phosphohexose or phosphoglucose isomerase. The other class that sometimes people, another name is once in a while people get confused and call it a mutase, but technically it is isomerase. It's reversible. There's nothing else that's really special about this one. Not like step 3. Dun, dun, dun. First of all, what's one thing that you should notice about step 3? ATP. Okay, and ATP goes to form what? ADP. What else can we notice right here already? The oxidation state is different. It adds a phosphate. I don't see the oxidation state being different. Okay, it adds a phosphate. Okay, what else is there? There's magnesium. We can make another observation too for step 3. Sometimes it states the simple things. We've added a phosphate at the expense of ATP. It utilizes magnesium. What else is it pointing to? Unlike the previous step. It's not reversible. This is the second checkpoint. Okay, so this is an irreversible step. All right. So, and by the way, this is one of my favorite enzymes to say. What class or classes of enzymes could this possibly be? There's only one that makes the most sense. Say it with some conviction. Kinase. And so if you were going to name this one, what would you name it? The pentokinase. Okay, I can see that. What else if we want to be a little bit more specific? What must it already have on it that for it to work that we've done in the previous two steps? A phosphate. Okay. Oh, now you're getting really, really, really close. Phosphofructokinase.
So it's basically just guess and see what happens, or write to.
Right?
when we're supposed to be writing the enzymes, like.
Well, once you start to use, if you call it phosphofructokinase, I'd give you the points for it. But they just drop the SE whenever it's all one word. Because once again, if you just was talking to someone and wrote down phosphofructokinase 1, and we're going to find out the reason why it's called 1. Because that means that there's more than one isoform, and one of them's in a certain place, and the other one's in another place. But they do the same type of reaction. But yeah, they also abbreviate this one as PFK, PFK1, phosphofructokinase, and it's a very, very important enzyme. Remember, there are only 3 checkpoints in glycolysis, and we've already covered 2. Okay? So PFK1 is step 3.
And you said they're rate limiting steps?
These are right. The checkpoints are where they are limited. We're going to talk about feedback inhibition and the way that they are limited. It becomes a little bit more complex for some of these than others. All right. So this is the key regulatory enzyme, or a key regulatory enzyme in glucose. It is a tetramer, which means what? 4 subunits that all come together in the quaternary structure. And it is subject to allosteric feedback, which allosteric was just a fancy word for...
Regulated.
Yeah, it's regulated. This is just due to feedback inhibition. We're going to find out that some of the products from later on in glycolysis go back and they inhibit. So that way you don't constantly keep breaking down your sugars. Okay? Because there are times that you want to store it for later on. As I mentioned, there are different isoforms. In particular, there's one that's called the muscle versus the liver, and you can make them up in different varieties. So M4 has all 4 of the subunits are for the muscle, L4 is all for the liver, and then you can have any variation thereof. So what is one possible product that would make sense overall in the big scheme of things, that would make sense whenever it would tell your body, okay, we have enough energy, we don't need you to keep breaking down the sugars? What would be the most obvious if you have a lot of it around that your body says, okay, let's relax and start storing sugar instead of breaking it down? No, not glycogen. That's the opposite. That's what you're storing it as. But what's the ultimate product? Ultimate product. No, energy product here. We're talking about ATP. So when you're high in ATP, it's going to deactivate this. Okay? If you're low in ATP, what do you suppose is going to happen? It's going to be activated. Okay?
It deactivates the phospho.
PFK1. Mm-hmm. All right. So then it should make logical sense. ATP inhibits it.
Okay, so this process makes ATP, but it mostly makes NADH to make more ATP.
Right. I mean, the overall goal in the very end of the process of going all the way down to carbon dioxide is you want to make more ATP, but it's just that directly in glycolysis you only make 2 ATPs. Net. We're going to find out what happens is you make 4, but you use up 2 in the process, and so it's energetic. It is energetic bookkeeping, so to speak. Also, it's inhibited by its own product, fructose 1,6-bisphosphate, which should also make sense. Just if you get a lot of fructose 1,6-bisphosphate, which would be like the abbreviation for it, sometimes they fructose 1,6. Sometimes they say BP. Sometimes they say P, for bisphosphate. Let you know that there are 2 of them. Then if you're not breaking it, if you already have high energy levels and you don't need any more, this will start to build up. Due to the what is that term that they use in biology? Like a bottleneck effect almost. And so then it'll also help shut down the enzyme that makes it. And so if we were looking at the energy diagrams, not energy diagrams, but the velocity, like what we've seen before, if there's high ATP, then we see this, what's this shape called? Sigmoidal. It becomes more and more sigmoidal. If you have low ATP, another way of thinking low ATP is high ADP, which should make sense. Then it becomes more, what's that shape called? Hyperbolic. Okay. All right. And so, and that fructose 6-phosphate in the bottom is this is just a fancy way of showing the Michaelis-Menten graph, V versus S. I shouldn't say fancy, it's just the specific one. Now we are up to reaction 4. We have fructose 1,6-bisphosphate, and it's going to make 2 of our friends that we're going to see a lot of throughout the semester. One of them is glyceraldehyde 3-phosphate. You should know the structure of this one because, just like the name implies, you start with glycerol. You turn 1 carbon into an aldehyde, so it becomes glyceraldehyde. And then on the other end, you make the alkyl phosphate. That's why it's glyceraldehyde 3-phosphate. The other one is dihydroxyacetone phosphate. And if you break it down, for those who have already had organic chem 2, if you break it down, you should already have been able to ascertain what that is, because acetone has 3 carbons, right? 1, 2, 3, and it's the simplest of what functional groups? Ketone. I mean, it's a 3-carbon ketone. So if it has dihydroxy, you just add an alcohol to each one, and then dihydroxyacetone phosphate is you turn 1 into the phosphate. So they also abbreviate this one rather than saying dihydroxyacetone phosphate. They give it a very hip-hoppy type of name. That's DHAP. DHAP. That is the technical term for it, hip-hoppy. So, all right. So this breaks or cleaves fructose 1,6-bisphosphate into 2 triose phosphates. And so from this point on, we're going to have to multiply. Well, technically from reaction 6 on, we're going to have to multiply everything by 2. You just have to remember that. This one, the name is a little bit more tricky. Of course, once you know it, it'll stick with you. But what class or classes of enzymes could possibly do this? So many times people say, oh, lyase. That may be true, but this one's got a special name. It's named after a class of compounds. What are some of the functional groups or classes of compounds on its products? Besides a phosphate and a ketone, what else do we have? What other functional groups do we have there? Aldehyde. What else is there? Alcohol. That glyceraldehyde 3-phosphate, just like we have enols, this is an aldol, and this is called aldolase. And so if you're doing matching and you come up to aldolase, then you're going to look for something that has an aldol in it, with hope. Pardon?
We're matching on the next test.
I won't say that there's always matching on, but sometimes there's matching on tests. Or what it is that I give a list of enzymes, and you have to tell me what metabolic pathway it's in.
So the dihydroxyacetone phosphate, the aldol is the
Those are
2
aldehyde.
and 3.
No, the aldol
Is
is, here, let me show you. See right here, there's an aldehyde. Next door is the alcohol.
right.
So it's called an aldol. Like an enol is an alkene that has an alcohol, and an aldol is an aldehyde with an alcohol. So, okay, this is one that I want you to know the mechanism for because it's been well studied. And so, here we go. We have the whole general acid, general base. So the first thing is upon binding is the ring breaks open. Because remember, that just happens normally. We've talked about that in organic chemistry and in biochem, how that there's that mutarotation. Rings break open and come back and all that kind of things. So it breaks open. But then we have an important lysine, and is that in the enzyme, and that lysine goes and smacks the carbon. So it's acting as a nucleophile. And then we have just a general acid that just helps it make that tetrahedral intermediate. Okay. Now, one thing that happens here that's important is called a Schiff base. Okay, and we're going to see this a lot. And lysines in particular can form these Schiff bases because they're electron sinks, and it's a free amine. And a Schiff base is just where you go from an amine to an imine. So what happens here is we have this tetrahedral. Oh, whoops! I hit the wrong one. We have this tetrahedral intermediate. Whoops! Let me get over. And here, instead of it getting collapsed of the tetrahedral intermediate, what we do is remember the lysine can have another lone pair of electrons, and it attacks that carbon twice, and so then the alcohol will leave as a water. I feel like doing some type of tribal dance next door.
One Direction, one was here. Oh, and a second.
That's really sad. You can just tell through the muffled wall.
Why are they singing again?
Is this vocal performance? Is this what we're building the
Oh my goodness. So then what we have that happens is a general base in the enzyme's active site goes and attacks the alcohol that's next door, that's adjacent. And this is why it's called the electron sink, is all the electrons then move towards that lysine. Whoops, I was about to attack this again. And so we have here, the general base takes the hydrogen off. Boom. So we're going to form the aldehyde of the glyceraldehyde 3-phosphate. But something that's a breaker give, and it's that bond between carbons 3 and 4 that goes towards the electron sink. It forms an alkene. One of the bonds breaks, and now you just have that single bond between the lysine and what will become the DHAP. Okay, the glyceraldehyde is gone. It's away. Then what happens here, is just a repeat of what we've seen. The lysine reforms the imine, and this swings out to take off a hydrogen to form the alcohol. And then one thing that the book doesn't show that I'm going to write on the board is that last step. And so we have lysine with its nitrogen double bond to the carbon. All the rest of the stuff doesn't really matter, so I'm just going to call it R rather than have to rewrite it all out. And then we have what will be the alcohol, or what is the alcohol, I should say. We have a water that comes in, which they do this a lot in biochemistry, where they just, since we're in vivo, we have lots of water around, so they don't always show, as you can see before, above, how the general acids and bases can just swap hydrogens all the time with the water. But we have a water that comes in, it attacks once, boom, this breaks off once. So then it is reversible. We have lysine. I'm going to show it glowing electrons. A lot of times I'll start with a hydrogen. It doesn't really matter in the sense because just like nitrogen will always want to make 3 to 4 bonds. It's protonated, it's 4. H2OH. Okay. But then, just like the lysine can attack it twice to form an imine, this oxygen will attack it twice, boom, and we get our enzyme back. So now we have our enzyme with the lysine that's free, and we have DHAP. And so it's just a general acid-base reaction that also has that shift base, that imine formation.
Is this one that we have to memorize?
Yeah, because we're going to see shift bases a lot. We're up to reaction 5. Now, reaction 4 is where it becomes bifurcated. So we have, and so the product at the end of reaction 4, we have the glyceraldehyde 3-phosphate. So glyceraldehyde 3-phosphate.
No.
And we have DHAP. Well, what's important here is glyceraldehyde 3-phosphate gets to skip 5. It goes directly to skip 5 to step 6. Can't hardly speak. DHAP has to become glyceraldehyde 3-phosphate so it can enter into step 6. All right.
Sing it the rest of the time. Sing it.
Oh my goodness. So I already kind of give this one because I forgot to cover it up. This one's by an isomerase. Okay, and sometimes they call it TPI because it's triose phosphate isomerase, which should make sense. Isomerase because of the fact that we're not changing the overall oxidation number states. We're just swapping the alcohol and the aldehyde, or I should say the alcohol and the carbonyl group. And so it goes backwards. We're going to see this one later on again. So 3 sugar has a phosphate. Okay. So at this point, I'm going to go ahead and I'm going to end class with prayer, and we're going to pick up with reaction 6 later on. Okay, so let me go ahead and